On behalf of Databricks, welcome to the Spark and AI Summit 2020. My name is Ghodsi. I'm the CEO of Databricks, and I'm looking forward to being your host over the next couple of days. We're excited to bring together 60,000 people from around the globe for what has quickly become one of the biggest data and AI events in the world. Now more than ever, Spark and AI Summit is truly a global community event. We've got an incredible lineup of speakers, content, and experiences planned for you this week. We have over 250 trainings, tutorials, lots of different sessions, both live and on demand. And I'm especially excited about our guest keynote lineup featuring people like Nate Silver from 538, Professor Jennifer Chase from UC Berkeley, Kim Hazelwood from Facebook, and Dr. Philip Atiba Goff, co-founder of the Center for Policing Equity. Also, please explore everything else that this virtual summit has to offer, including our developer hub, advisory lounge, and much more. You can find it all in the left nav of your virtual summit dashboard. Also, I want to take a moment to thank all of the organizations who are helping put this event on. We wouldn't be here and we couldn't pull this off without these important sponsors. Please make sure to pay them a visit in the Dev Hub of the Expo. With that, I want to spend some time talking about why this event is so important to us. At Databricks, our mission has always been to help data teams solve the world's toughest problems. This is a mission that we share with the entire data community. Nobody understands the power and vast potential of data and AI like this group. And this event is a great manifestation of that. It's an incredible opportunity to learn from each other, share new ideas, and move the industry forward. And today, I'm sure you'll all agree that solving the world's toughest problems has never felt more urgent. As an example, racial injustice continues to be a systemic issue that is impacting the lives of so many. Recent events and protests around the world remind us that individuals, organizations, and governments must continue to do more to bring awareness to racial injustice and drive meaningful change. While it's of course so much more than a data problem, some organizations are using data science to tackle some of its systemic roots. A great example is the Center for Policing Equity. The Center for Policing Equity uses data science to reduce the cause of racial disparities in law enforcement. They use advanced analytics to diagnose gaps in policing and help police build healthier relationships with the communities they serve. I hope you all attend the afternoon keynote sessions, especially the one where CPE co-founder Dr. Philip Atiba Goff will talk about the important role that the data community can play in addressing racial and social challenges. We are inspired by the work that the Center for Policing Equity is doing and have decided to sponsor them here at the Spark and AI Summit. In addition to CPE, we've also decided to sponsor the NAACP Legal Defense and Educational Fund. The NAACP was formed over 100 years ago, and its Legal Defense and Educational Fund has emerged as one of the country's best legal organizations that fights for justice on behalf of the African American community. Through litigation, advocacy, and public education, LDF seeks structural changes to expand democracy, eliminate disparities, and achieve racial justice. So in order to support both of these organizations, we're setting an ambitious fundraising goal for this event. With your help, we want to raise $100,000 by the end of this event. We made it super easy for you to donate at any given time by clicking Donate Now button on your navigation panel. But I'm also really happy to share that Databricks will match all donations up to $100,000. So I sincerely hope you'll consider making a contribution. It would be amazing if we together could raise $200,000 over the next few days. When we talk about solving the world's toughest problems, it's also hard not to think about the disruptive impact of COVID-19. The virus itself is, of course, a massive problem, but so are the many issues associated with mitigating its impact. Not to mention the lasting impact it will have on entire industries, on where and how we live, and the global economy. We are living in unprecedented times, but what inspires me personally, and hopefully it inspires all of you, is the role that we can all play in solving problems like the ones we face today. More than ever before, this is our time. It's the data community's time to unlock the full potential of data and AI. But why now? Well, one, because the world understands and acknowledges that potential more than ever before. Two, because technology has evolved and things are possible now that were unimaginable only a couple of years ago. And third, because as a data community, we're more than ready, willing and capable than we've ever been before. As it relates specifically to the COVID crisis, it has been inspiring to see how data teams are answering the call. As an example, Rush University Medical Center is one of the top-ranked hospitals in the United States. They are doing data analytics services for capacity tracking across multiple hospitals in Chicago. What stands out about their story is how they were able to build this so quickly across multiple hospitals with multiple data teams and multiple data sets. This probably wouldn't have been possible a couple of years ago. And while technology advancements have a lot to do with this, it also has a lot to do with how projects like this are tackled. And at Databricks, what we've learned from working with organizations like Rush is that data and AI is a team sport. Every company wants to be a data company. And if you think about it, what that actually means, it requires a new way of empowering people working with data, enabling them to organize around the data they need, collaborate, and get to the answers they need more quickly. It's about the right people coming together with the right data as quickly as possible. Unfortunately, most organizations aren't able to operate this way today. Most data teams aren't set up for success because they're stuck in silos defined by closed and proprietary systems. They're working with fractions of the data that they need, often incomplete or inconsistent. They spend more time chasing data, looking for latest versions, figuring out who can give them access, and not nearly enough time exploring, analyzing, or deriving value from it. So in order to succeed, data teams need to evolve. They need to evolve from being separated by data to being unified by data. Agile, dynamic, connected to each other so that they can move fast and do their best work. And that's why our theme for this year's conference is Data Teams Unite. It's a call to unite around the data. Unite to do our best work and help others do theirs. Unite to innovate faster, and to do so at a time when the world needs it the most. In fact, we technically launched this theme a couple months ago with our Data Teams Unite hackathon. In it, we asked data teams to come together and innovate for social good by focusing on solutions to help address the COVID-19 crisis, climate change, and social issues in their communities. As prizes, Databricks will be making donations to the charities of the winner's choice. $5,000 will go to the third place, $10,000 to the second, and $20,000 to the first. We've received a number of great submissions, and I will announce the winners in tomorrow morning's opening keynote. Please don't miss it. Data Teams Unite also captures the spirit of this event and of the open source data community. Bringing data teams together has long been the vision of Apache Spark, and it's been really exciting to watch the evolution of this community. In fact, this year, Apache Spark turned 10 years old, and there's nobody better suited to talk about it than the guy who created it, Matei Zaharia. Matei, happy 10 years old.
Oh, thanks, Ali. This looks great. So today's a very special year for Apache Spark. Spark 3.0 is out, but it's also 10 years since the first open source release of Spark. So I want to talk to you today about what got us here with the open source project and what did we learn in the process that we're using to contribute to Apache Spark development in the future. And to do that, I'll start by telling you my story with big data, how I got into this space when I started my PhD at UC Berkeley. So I started my PhD in 2007, and I was very interested in distributed systems. I had actually been working on peer-to-peer networks before this, but I wanted to try doing something different. And as I looked around at what's happening in the industry, I got very excited about data center scale computing. These large web companies were starting to do computations on thousands of machines and store petabytes of data and do interesting things with them. And I wanted to learn more about these, and so I actually worked with some of the big data teams at Yahoo and Facebook early on. And in working with these, I realized that there's a lot of potential for this technology beyond web companies. I thought this would be very useful for scientific data sets, industrial data sets, many other things. But it was also very clear that working with them, these technologies were too hard to use for anyone who was not at a large web company. In particular, all the data pipelines to use these technologies had to be written by professional software engineers. And also all the technologies were really focused on batch processing. There was no support for interactive queries, which is very important in data analysis, no support for machine learning and advanced algorithms. And when I came back to Berkeley after spending some time working on these, I also found that there were local research groups who wanted a more scalable engine for machine learning in particular. So I thought this was a great opportunity to try building something in this space. And in particular, I worked early on with Lester Mackey, who was one of the top machine learning students at Berkeley in my year, and who was on a team for the Netflix prize competition, this $1 million competition to improve Netflix's algorithm. And so by seeing the kind of applications that he wanted to run, I started to design a programming model that would make it possible for people like Lester to develop these applications. And I started working on the Spark engine in 2009. Now, once I started the work, the feedback on it was great. These machine learning researchers at Berkeley were actually using it. And so we decided to open source the project in 2010. And this is what the initial version of it looked like. So it was a very small open source project, really just focused on MapReduce style computing with a cleaner and faster API. But the exciting thing is that within 2 months of us open sourcing it, we started getting pull requests from other community members. So there were really people picking this up, trying to use this very early project and doing interesting things with it. And so we spent the next 2 years working with early users in the Bay Area. I spent a lot of time actually visiting these companies and organizing meetups and trying to make this a great platform for large-scale data processing. And in working with these early users, we were blown away by some of the early use cases. People were doing things that we as researchers had never anticipated, and we thought that there's the potential to do a lot more here. So, for example, some of the early users were powering interactive operational apps like a user interface using Spark on the backend. For example, there was a group of neuroscientists at Janelia Farm that were monitoring data from the brains of animals and other sensors in real time while they're running neuroscience experiments and building that up using Spark. That was something we had never anticipated. It's obviously very cool to be able to build these operational apps for exploring large data sets. Another interesting group was from this startup company, Quantifind, that had built a product for its customers to analyze social media and other data sources. And they actually were using Spark to update data sets in memory and implement streaming computation. This was before we added a streaming engine to Spark. So they had just built streaming computation on this platform. And finally, there were groups in industry, for example, Yahoo's data warehousing group that were running SQL queries over Spark or R data science workloads and other workloads. And they were opening up the Spark engines to tens or even hundreds of more users than we initially had been targeting. So based on these use cases and what Spark was able to do for these companies, we spent the next few years really working on expanding access to Spark, making sure that anyone who works with data can somehow connect to this engine and be able to run computations at scale. And there were 3 major efforts there. The first one was around programming languages. So we developed Python, R, and SQL interfaces to Spark that today are by far the most popular ways of using the engine. The second was around libraries. We wanted to have great built-in libraries for machine learning, graphs, and stream processing, and these provide a lot of the value of the platform today. And finally, we also got a lot of feedback on the API, what users found difficult, for example, how to set up map and reduce and other operators to do a distributed computation. And we decided to make this big change to the high-level API called data frames, which runs most of the APIs in Spark on top of the Spark SQL engine. So you get the same kind of optimizations and query planning that a SQL engine will do, but in these easy-to-use, programming language interfaces. And that quickly became the dominant way to use Apache Spark. So if you look at Apache Spark today, these changes have all had a huge impact on the project. Let's start with support for Python. Among the users of interactive notebooks at Databricks, where we can measure this, 68 of the commands coming into the platform are in Python. This is more than 6 times the amount of Scala. It's by far the most widely used programming language on Databricks today, and it means a wide range of software developers are able to connect their code to Spark and execute it at scale. Interestingly, the next most common language in notebooks is SQL. There's also a similar amount of commands to the total that we have in notebooks is just coming in through SQL connectors directly. So that's also very widely used. Now, next thing is SQL. So even when developers are using Python or Scala, about 90% of the Spark API calls are actually running on Spark SQL through these data frame APIs and other APIs, which means they benefit from all the optimizations in the SQL engine. And just on Databricks alone, we're seeing exabytes of data queried per day using Spark SQL. As a result, the community has invested a lot in the Spark SQL engine and making it, one of the best open source SQL engines on the planet. So for example, this plot here shows the improvement in performance on the TPC-DS benchmark, the leading benchmark for data warehousing workloads. And you can see with Spark 3.0, Spark is now running 2 times faster than the previous version, and also about 1.5 times faster than Presto, very highly regarded SQL engine for large-scale data sets. And another exciting piece of news that happened with SQL this year is that earlier this year, Alibaba set a new benchmark for the TPC-DS, a new record for the TPC-DS benchmark using the Spark SQL engine to exceed, the cost performance of all the other engines that have been submitted to this benchmark. So it's really the basis of very efficient and powerful SQL engines today. And the final one I want to talk about is streaming. Just on Databricks alone, we see about 5 trillion records per day processed with structured streaming, which makes it super easy to just take a data frame or SQL computation and turn it into a streaming one. And this number has been growing by close to a factor of 4 year over year. So we're seeing very fast adoption of this high-level streaming API. Okay, so given these changes of the project, what are the major lessons that we learned? For me, at least, there were 2 big lessons. The first one is to focus on ease of use, prioritize that for both data exploration and production. We found that a lot of the applications that people built quickly became these operational apps or streaming apps or repeated, reports, and we wanted to add a lot of features into the engine to make it easy for these to keep going and to tell you, if something changes or something breaks in a way that's easy to fix. So a lot of the work in Spark now is to make that super easy. The second big lessons we had was to really design the system around APIs that enable software development best practices and integrate with the broad ecosystem. So we designed all the APIs in Spark so that they fit into standard programming environments like Python and Java, and so that you can use best practices like composition of libraries into an application, testability and modularity, and you can build packages that a user in your company can safely use to do a computation or have this wide open source community around them. And this is something where we've done a lot of improvements over time as well. Okay, so given these lessons, what's happening in Apache Spark 3.0? This is our largest release yet with over 3,000 patches to the community, and it's actually designed to be easy to switch to from Spark 2. So we definitely encourage you to check it out and switch to it when you can. This chart here shows where the patches have gone, and you can actually see almost half the patches are in the Spark SQL engine, both for SQL support itself and because it's the underlying engine for all these data frame API calls. So this is the most active piece of development, but there's of course a lot else going on as well. So I just want to highlight a few of the features that I'm excited about, focusing specifically on SQL and Python, but of course, there's quite a bit of other stuff going on in 3.0 as well. And I'm going to start with a major change to the Spark SQL engine, the largest change in recent years, which is called adaptive query execution. So this is a change where the engine can actually update the execution plan for computation at runtime based on observed properties of the data. For example, it can automatically tune the number of reducers when doing an aggregation or the join algorithms, or it can even adapt the skew in the data to plan the computation as it's going. And this makes it much easier to run Spark because you don't need to configure these things in advance. It will actually adapt and optimize based on your data, and also leads to better performance in many cases. So to give you a sense of how it works, let's look at a simple example of setting the number of reducers. We found that today about 60% of clusters, the users tune the number of reducers in them. So that's a lot of manual configuration that we want to eliminate and automate. And so with AQE, what happens is after Spark runs the initial phase of an aggregation, it actually observes the result size. You can have some number of partitions there, and it can set a different number of partitions for the reduce. For example, coalesce everything down to 5 partitions and optimize it for the best performance based on what kind of data came out of that aggregation. Now, even more interesting things happen with joins and more complicated operators. For example, when you're joining two tables, even if you have high quality statistics about the data, it's hard to know how many records will end up before the join. And using AQE, Spark can actually observe this after the initial stages of the join have happened, and then choose the join algorithm that best optimizes performance downstream. And in fact, it can adapt both to the size of the data and to the skew around different keys. So you don't have to worry about treating skewed keys in a special way anymore. And these results in really big speed-ups on SQL workloads. So for example, on TPCDS queries, we've seen up to a factor of 8 speed-up with AQE. And even better, it means you can actually run Spark on a lot of data sets even without pre-computing statistics and get great performance because it discovers the statistics as you go along. Okay. That's just one of the changes that affects both SQL usability and performance. There's quite a bit more. So on the performance side, we have dynamic partition pruning, query compile time speedups, and optimizer hints. And as I said earlier, these have led to a 2x reduction in execution time for TPCDS and a lot of improvements on real workloads. And finally, there's been a big effort in 3.0 around SQL compatibility, in particular an ANSI SQL dialect that follows the standard SQL convention in many areas of the language, and that makes it very easy to port in workloads from other SQL systems. And this is one of the areas that we're continuing to invest in, but we've made significant strides in 3.0. Okay, so that's a bit about SQL. The other thing that I wanted to highlight is around Python. So we've done quite a bit of work on both Python usability and performance. For usability, we've made it much easier to define pandas user-defined functions using type hints in Python, which let you specify the format of data you expect. So in Spark, it's easy to make a function that takes in batches of data as pandas series or data frames, for example, or even as an iterator of series, and you can just specify these with type hints. For comparison, the previous API required you to write a lot of boilerplate code in order to say what kind of input your function expects, and that was very error prone. So now that can go away, and it's super straightforward to define and use these functions. There's also been a lot of work on performance using Apache Arrow. We're seeing about 20 to 25% speedups in Python UDF performance using the latest enhancements in Apache Arrow, and also up to a 40 times speedup in Spark R by using Arrow to exchange data between R and Spark. And these are all transparent to the end user. You just upgrade and you get these speedups. And we have quite a few new APIs for combining pandas with Spark as well. And finally, there are features throughout the engine, including a new structured streaming UI for monitoring computations, a way to define custom observable metrics about your data that you want to check in streaming jobs, a SQL reference guide, and a powerful new API for data sources. So if you want to learn more about Apache Spark 3.0, I invite you to check out Xiaoli's talk at this summit and many of the talks on these individual features. And the Spark project itself is not the only place where things are happening. There's actually a broad community around it, and I wanted to highlight some of the changes. So at Databricks last year, we released Koalas, which is a pandas API that can run directly over Spark to make it very easy to port workloads. And that's evolved a lot in this year. I'll talk about it. Of course, there's Delta Lake for reliable table storage. And we've also done quite a bit of work to add Spark as a scale-out backend in popular libraries, including scikit-learn, HyperOpt, and JobLib. So if you use these for machine learning, you can just scale out your jobs on a Spark cluster. We're also collaborating with Regeneron to develop GLOW, a widely used library for large-scale genomics. And NVIDIA has been developing RAPIDS, which provides a wide range of data science and machine learning algorithms that you can call from Spark that use GPU acceleration and really speeds up these workloads. And finally, we've also done a lot of work on Databricks on improving connectivity with both commercial and open source visualization tools so that users can build interactive dashboards using Spark as the backend. So I'll just dive into some of the changes in Koalas specifically. If you're not familiar with Koalas, it's an implementation of the Pandas API over Spark to make it very easy to port data science code in this really popular library. We launched it actually a year ago at Spark AI Summit, and it's already up to 850,000 downloads per month, which is about a fifth the total downloads of PySpark. So we're really excited with how the community has adopted this library. And we're investing quite a bit more into Koalas. And at this event, we're actually excited to announce Koalas version 1.0. This new release has close to 80% of the API coverage of Pandas. It's also quite a bit faster thanks to the improvements in Spark 3.0, and it supports a lot of features that were missing before, including missing values, NAs, and in-place updates. And it's also got faster distributed index type. It's very easy to install Koalas and PyPy and get started. And if you're a Pandas user, we believe this is the easiest way to migrate your workloads to Spark. So that's enough of me talking. We also like to show you demos of all these new things. And I'm really excited to invite Brooke Wenig, the machine learning practice lead at Databricks, to give you a demos of the new features in Koalas and Spark 3.0.
Hi, everyone. These are some crazy times. And while we're all still social distancing, many of us are staying at home trying to figure out, what are we going to cook for dinner tonight? I know my whole SF office has gone through the banana bread and sourdough craze, but now I need some new recipes to impress our coworkers with on our food Slack channel. In particular, we need to find a recipe for Matej. Matej is a very busy person who loves to optimize everything. Given the increase of people contributing recipes, we now have millions of recipes that we need to analyze in a scalable manner so that Matej can make a data-driven decision on what he's going to prepare tonight. Along the way, we'll explore some new features in Spark 3.0 and Koalas. Let's get going. Like any data scientist, I'm going to start off with some exploratory data analysis with Pandas. Pandas is a great way to get started with exploring your data because it's simple to use, has great documentation, and a fantastic community. Let's go ahead and visualize this subset of our data. You can see here that our recipes data contains the name of the recipe, when it was contributed, nutrition, ingredients, etc. However, we don't just have one file, we have a whole directory of Parquet files we need to read in. So let's go ahead and load in our entire data set with Pandas. Unfortunately though, Pandas wasn't prepared to handle the rising recipe count. So if we allow this query to continue on, it'll crash trying to load in 30 gigabytes of data onto a single machine. Let's instead cancel it. Now let's use Koalas to load in our data set instead. Koalas provides the Pandas-like syntax and features that you love, combined with the scalability of Apache Spark. To load in our dataset with Koalas, we simply replace any of the PD logic with KS for Koalas. And now you can see just how quickly we can load in our entire dataset with Koalas. But let's say Matej's pretty busy tonight, and he wants to find a recipe that takes less than 30 minutes to prepare. You can see I've already written the Pandas code to filter out for recipes that take less than 30 minutes, and then visualize the distribution of the number of steps these recipes take. To convert it to Koalas, I simply replace my Pandas data frame with my Koalas data frame. And voila! I no longer need to downsample my data in order to visualize it. I can finally visualize big data at scale. We can see here the distribution of the number of steps. While most recipes take less than 10 steps, you can see the x-axis extends all the way out to 100. There's a universal muffin mix that takes 97 steps to prepare. Matej won't be cooking that one tonight. In addition to our recipes data, we're also interested in the ratings for those recipes. Because Koalas runs on Apache Spark under the hood, we can take advantage of the Spark SQL engine and issue SQL queries against our Koalas data frame. You'll see here that we have our ratings table. Now we want to join our ratings table with our recipes table. And you'll notice I can simply pass in the Koalas data frame with string substitution. Let's go ahead and run this query. Wow, we can see that this query took over a minute to run. Let's see how we can speed it up. I'm going to copy this query and move it down below. After I enable adaptive query execution. With adaptive query execution, it can optimize our query plan based on runtime statistics. Let's take a look at the query plan that's generated once it's enabled. I'm going to dig into the Spark UI and take a look at the associated SQL query. Here, we can see that it passed in a skew handling hint to the sort merge join based off of these runtime statistics. And as a result, this query now takes only 16 seconds for about a 4x speed up with no code changes. In addition to using Koalas to scale your pandas code, you can also leverage Spark in other ways to scale your pandas code, such as using the pandas function APIs. We're going to use the pandas function APIs to apply arbitrary Python code to our data frame, and in this example, we're going to apply a machine learning model. After seeing that universal muffin mix take 97 steps in 30 minutes, I'm a little bit skeptical of the time estimates for these recipes, and I want to better understand the relationship between the number of steps and ingredients with the number of minutes. As a data scientist, I built a linear regression model in our dataset using scikit-learn to predict the time that a recipe will take. Now I want to apply that model in parallel to all records of our data frame. You'll notice here just how easily I can convert our Koalas data frame to a Spark data frame. To apply our model, I'm going to use the function called map_in_pandas. Map_in_pandas accepts a function you want to apply with the return schema of that data frame. The function I want to apply is called predict. Predict accepts an iterator of pandas data frames and returns an iterator of pandas data frames. I'm then going to load in our model. If your model is very large, then there's high overhead to repeatedly load in the model over and over again for every batch in the same Python worker process. By using iterators, we can load the model only once and just apply that to batches of our data. So now let's go ahead and see how well our model performs. We can see here that the predicted minutes is pretty close to the number of minutes for some recipes. In this case, the true number of minutes is 45, we predict 46, or the true value is 35, we predict 39. But in some cases, our time estimates are a bit off. And we can actually see in the description, don't be dissuaded by the long cooking time. So Matej's decided he doesn't want to cook anything tonight, he just wants to make a smoothie with the shortest preparation time. So Matej, which recipe will you be preparing? Looks like Matej will be preparing a berry smoothie with only 4 ingredients and a grand total of 0 minutes. Wow, he's really optimizing for speed. Stay tuned for a very delicious surprise.
Wow, thanks, Brooke. That was an amazing demo, and the smoothie turned out delicious. It's great. One other announcement I wanted to make that also ties into Brooke is that we've been working to publish a new edition of Learning Spark, the popular book from O'Reilly. Brooke is one of the co-authors, actually, and we're giving away a free copy of the ebook to every attendee at the summit. So we invite you to check this out if you want to learn about the new features in Spark 3.0. Okay, and then the final thing I want to end on today is what's happening next in the Apache Spark ecosystem. If we step back and look at the state of data and AI software today, it's obviously made great strides over the past 10 years, but we still think that data and AI applications are just more complex to develop than they should be. And we think that we can make that quite a bit easier, and we have a lot of ongoing efforts in open source Apache Spark to do this, building on these 2 lessons, ease of use in exploration and production, and APIs that connect with the standard broad software ecosystem. So I'm just going to briefly talk about 3 big initiatives that we are working on at Databricks for the next few versions of Spark. So the first one is what we're calling Project Zen. The goal is to greatly improve Python usability in Apache Spark. Because it is the most widely used language now, we want to make sure that Python developers have a fantastic experience that's familiar with everything else that they do in Python. And there are quite a lot of areas where we think we can improve the experience. We've called this Project Zen, by the way, after the Zen of Python, the set of principles for designing Python that have led to it being such an amazing environment today. So some of the things we're working on are better error reporting, porting some of the API changes from Koalas. We got to experiment with them there, and we think they're useful enough that we want them to just be part of Spark. Improve performance and Pythonic API design for new APIs. I'll give a few examples of what we're doing with this next. We also have a continued initiative around adaptive query execution. We've been really pleased with what it's doing so far, and we think we can cover more and more of the SQL optimizer's decisions adaptively and really dramatically reduce the amount of configuration or preparation of the data needed to get great performance with Spark. And finally, we're also continuing to push on ANSI SQL. The goal is to run unmodified queries from all the major SQL engines by having dialects that match these. And we think we've been working a lot with the community to build these, and we think it will provide a lot of benefits in Spark. Just to give you a couple of examples of the Project Zen features, one of them is around error messages. So if you run a Python computation today and you have an error on your worker process, such as dividing by 0, you get this very scary looking error trace in your terminal. Lots of stuff going on. And if you look at it closely, there's a lot of Java stuff, and maybe you can see part of the error trace is actually about the problem that happened in your Python worker, which in this case was division by 0. But it's pretty unfriendly, especially if you're just a Python developer. It's hard to see exactly what was going on. So as part of Project Zen, we're simplifying the behavior in Python of a lot of common error types, so that if it's a Python-only error or a SQL planning error, you see a very small message that lets you directly fix the problem. So you can see this has just the Python-relevant bits of that error, and you can see that there is a division by 0. Of course, this might be a bad example because if you really accept Project Zen, you will come to a much better understanding of emptiness, and you will probably never get divisions by 0 again. But it's just one example. And then the second change I want to show is a new documentation site for PySpark that's designed to make it really easy to browse through, find Python examples, and it's built on kind of the latest best practices for Python documentation. And we think this will make it easier to get started for many of our users as well. So these are some of the changes. We're really excited about what's next for Apache Spark, and we look forward to seeing what you do with it. Back to you, Willie.
Thanks, Matej. So with Spark 3.0, we've now added broad support for SQL. We've also integrated it with Python. And in some sense, it's really unifying now SQL analytics, or data warehousing, and data science. And that's really exciting because that's where we think the future is going. In fact, our customers were unifying these two things for a while. And actually, a pattern has emerged in which they call this the Lakehouse paradigm. So I want to talk a lot about that today. But before I dive into the details of the Lakehouse, I want to provide you some context of why we need it. So data warehouses were built 40 years ago, and they were purpose-built for BI reporting, and they worked really great for that. However, they don't have any support for video data, audio data, and text data, which is a lot of the kind of data that we have today. And as a result of that, it's very hard to do data science or machine learning on these data sets in the data warehouses. Also, they have limited support for real-time streaming, which is becoming increasingly important. And finally, they're closed and proprietary formats. So the data is either locked in a data warehouse, or you have to take it out if you want to operate on it with other tools. Therefore, today, most of the data is actually first stored in a data lake or a blob store, and a subset of it is moved into a data warehouse. So let's look at these data lakes. So the data lakes, they're great in that they can handle all your data now, and you can do data science and machine learning on it. However, they're bad at exactly the things that the data warehouses were good at. So they have really poor BI support. They're very complex to set up and configure. You need advanced data engineers to do that. And then once you start using them, if you try to do BI ever on a data lake, you're going to find out that the performance is really, really bad. Hence, as a result, what we're seeing is that a lot of these data lakes have turned into unreliable data swamps. And actually, most organizations, unfortunately, have to have both of these things side by side. So that is why we believe in the Lakehouse paradigm. The Lakehouse paradigm brings the best of both these worlds. You get the structure, you get the BI and reporting advantages of data warehouses, and you also get the data science, machine learning, AI, and real-time capabilities of data lakes on all of your data. In fact, the Lakehouse is distinct from data lakes. It actually starts out like a data lake, so it looks at the bottom layer like a data lake, but the crucial difference is that it has something that we call a structured transactional layer. This layer brings quality, structure, governance, and performance to data lakes. And at Databricks, we believe that open source Delta Lake project is a great way to get structural transactional layer on top of your data lake. So I'm going to talk a little bit about this next. So before I go into the details of the Delta Lake open source project, I want to tell you a little bit about its history and how it came about. So Delta Lakes are built on top of data lakes. And as we know, data lakes, they're great. They're really cheap. In fact, they have 10 nines of durability. They can scale infinitely. They also can store now all kinds of data, video, audio, text. You can also store structured, semi-structured, and unstructured data in these. And finally, they're based on open standardized formats. In recent years, we've seen in particular the Parquet format becoming the standard in this ecosystem, and lots of different tools can now directly operate on these Parquet files. So that's awesome. And as a result of this, organizations have now been promised that if they just build a data lake, they can get all these benefits. They can get real-time analytics, they can get data science, they can get machine learning, they can get data warehousing, reporting, BI, everything. So they've been very excited. They've built up these data lakes. Unfortunately, though, most of these projects are actually failing. And at Databricks, we started to actually see lots of demand for professional services. And we had to put our own solutions architect on these customers to look at what's the problem that they're facing. And what we did is we rank ordered the problems that we have to address with these customers. And I'm going to walk you through each of these problems. So there's 9 of them in the order of sort of severity that we saw. And then I'm going to talk about how we address them with the Delta Lake project. Okay. So the first problem that we actually noticed that is happening over and over again is actually a very trivial, simple problem. But it's actually that we were getting pulled in and customers were saying we have a hard time appending new data into the data lake while at the same time correctly reading it. Turned out some of the new data comes in. If you try to read it at the same time, because of eventual consistency, you might not see the results. So our solutions architects were creating copies of the data in different directories and switching it over when it was ready. Needless to say, this was really complex and costly. Second, modification of existing data is really difficult with data lakes. And this is exacerbated when companies are trying to satisfy GDPR or CCPA. So in GDPR and CCPA, if a customer says, I don't want you to store any records in your data sets about me, you have to go and scrub those and delete those. Well, that's really hard with traditional data lakes because they're basically batch-oriented systems. So you have to run a big Spark job all over your data set once a week to scrub it to make it compliant. This was, again, extremely costly. Third, some of our customers were having problems that were hard to diagnose. After we looked into the logs and did diagnosis, it turns out that many years back, maybe some Spark job failed halfway through. Some of the data that it was ingesting had made it in, the rest was missing. And as a result, the whole project was failing. 4, real-time operations are really hard on data lakes. This is a special case of problem number 1, but mixing real-time streaming with batch led to inconsistencies. In particular, if you're appending new data in batch operation, but at the same time in real time you're trying to read it, you're going to have problems. And this one is actually hard to solve. It's not just to copy files or copy directories. 5, organizations want to keep historical versions of their data. Especially regulated environments, you have to reproduce your data sets because there's auditing and governance that happens. So here again, the poor man's version was keep copies of all your data sets in different directories with different date names. Very costly. 6, difficult to handle the metadata itself. Now, as these data lakes were growing, the data itself was growing into petabytes. The metadata for these systems was itself now becoming terabytes in size. And as a result of this, the catalogs that were storing the metadata were falling over, they were not scalable, so we were pulled in to do professional services again to fix that. 7, the too many files problems. Because data lakes were file-oriented, you could end up in a situation where you had millions of tiny files or a few gigantic files, again, leading to lots of problems when you were trying to consume it. 8, it was hard to get great performance. Because you're just dumping your data into the data lake without thinking about how it's going to be used later, how do you know if the data layout is sort of optimized for the performance that you need later? And finally, the most important problem, in my opinion, but a hard one to actually know, was data quality issues. It was constant headaches where customers would pull us in, and it turns out that the data was changing in a subtle way, or the semantics was changing over time, or all of it wasn't there. So this was leading to all kinds of problems with these projects. So at Databricks, we wanted to take an opinionated approach. We said, we want to build a system that from the get-go tries to get all these things right so that we don't have to ever configure them or ever have to address these issues ever again. So the Delta Lake open source project addresses this by adding massive reliability, quality, and performance to your data lake. And the way it does it is by bringing the best of data warehousing and data lakes to one place together. And finally, it's based on open source Parquet format, so you can keep all your data on your data lake in this open source format with all these benefits. So how does it do this? So these were the 9 problems that I mentioned earlier, and I'm going to go through each of these and mention how we actually address this with the Delta project. Well, luckily, it actually turns out the first 5 problems can all be addressed with the same technique. By having a transaction log that stores all the operations that you're doing on your data lake, you can actually now make it fully atomic. That means that every operation that you do on your data lake either fully completes or it aborts and cleans up any residue, and you can try it later. The way that actually happens is that there is a Delta log, and it stores every operation. So for instance, here we have an example where one operation is adding 2 files, 2 Parquet files. They will atomically be added. Then after that, maybe that first file is deleted and a 3rd file is added. The key thing here is that Delta always makes sure that each of these are happening as if it was sequentially executed. Okay, so that's awesome. Now we can make sure that 1, if we're appending new data into the system, it's always either going to be there or it's going to be canceled, and you can read it at the same time. You won't have any issues. 2, modifying existing data if you want to get GDPR or CCPA compliance actually is really easy now because transactions enable you to do fine-grained upserts. So you can go in and modify small data in your data set in a transactional manner. Jobs failing midway, that also goes away because the job either fully succeeds or fully is aborted. And then real-time operations, it's the same thing. All operations, whether real-time or batch, are consistent with the transaction log. And now, finally, because we have all the deltas of all the operations that happened on your data set, we can actually implement something called time travel. Time travel lets you submit queries and then say, I want the answer to this as of the time 2 years ago. And it gives you the response as if the query was submitted 2 years ago. So this is great now for compliance and governance. Okay, so that's awesome. Now we solved those first 5 problems. How do we deal with the metadata problem? The fact that metadata is getting large and the catalogs are falling over. Well, luckily it turns out that there's a project called Apache Spark, and it's really, really good at large-scale parallel operations. So under the hood, we use Spark, and all our metadata is stored in Parquet format right next to the rest of your Parquet files. That way, you can actually move your data from one place to another by just copying the data. You don't have to worry about catalogs that are out of sync with the data that you have. So that's awesome. So okay, now we can scale the system with the Delta Lake project to really large metadata. What about the too many files problems? Well, the too many file problems and the performance problems that we're seeing with data lakes, we now automatically fix those because we automatically optimize the layout of your data. How do we do that? Well, a bunch of indexing techniques. 1, we partition, of course, your data. But 2, we also do data skipping. Data skipping enables you to prune the files based on statistics that you have on numerals. So you know exactly what's the max and the minimum of every data that you have in the files so that you can actually avoid reading a lot of the files when you get a query. And then finally, we have something called Z-ordering. Z-ordering actually enables you to optimize multiple columns at the same time. So if you have a year, month, date index, you now can actually search on just date, and it can be as fast as if you searched on year, which is hard with partitioning. Okay, so this is awesome. Now we get all these advantages that we had in data warehouses as it comes to performance. What about the last problem, the most important and the hardest problem, the quality issues? Well, it turns out that we can actually solve that with schema validation and evolution. So all data in Delta tables have to adhere to a strict schema. It can be a star schema, a snowflake schema, but as soon as you have the schema, we make sure that all your data 100% adheres to this schema. If any data appears that's not satisfying the schema that you have, we actually put it on the side in a quarantine that you can then look at, you can clean it up, and when you cleaned up the quarantine, the data makes it back into Delta. But now you know that all your data in a Delta table is always pristine. Okay? And finally, we've actually added something called Delta expectations. Delta expectations is a novel way in which you can actually express quality expressions using SQL or user-defined functions, UDFs, where you can specify pretty much any business logic for quality that you like. And now we guarantee that your table satisfies all those quality metrics always. And with expectations and schema validations, the pattern that we're seeing our customers use in data lakes is that they're actually now creating a curated data lake. The curated data lake now has bronze tables where you might have the raw data coming in, and then that gets refined into filtered, cleaned, and augmented tables that we call silver tables. And then finally, the most optimized business level aggregated data sets are in so-called gold tables. And those are the ones that you're really sort of serving into your BI needs. So zooming out, the Delta Lake project solves the problems we had with the data lakes using 4 techniques. First, it uses ACID transactions. Second, it uses Spark under the hood to get the scale for the metadata. Third, it uses indexing and lots of different indexing techniques to get speedups that we traditionally used to have in data warehouses. And then finally, it uses schema validation and expectations to get the quality that we expect to have if we're using a data warehouse. We really want this to become the standard for how people create their lakehouses. So as a result of this, we've made this project work well with all these other systems. So you can now actually read and write both from Delta and Hive and Spark, Presto, Amazon Redshift, Amazon Athena, and Snowflake. And creating data with Delta is really easy. In SQL, instead of saying using Parquet, you just now in SQL say using Delta, and you're just using Delta. So with Delta Lake, we are able to fill in critical layer of the modern lakehouse architecture, bringing structure and reliability to your data lakes in support of any downstream data use case. But from a performance perspective, indexing alone isn't enough. For many analytic workloads that involve small queries that need to be executed very fast, you need more. You want a high-performance query engine that can deliver the performance required for traditional analytic workloads. I'm pleased to announce that at Databricks, we've been working on a solution that we're calling Delta Engine. So I want to welcome on stage Reynolds Shin, co-founder and chief architect of Databricks, and he's going to tell us what Delta Engine looks like under the hood.
Thank you, Ali. I'm really excited to be talking to you today about Delta Engine, a high-performance query engine for Delta Lakes. Delta Engine builds on Apache Spark 3.0 and is fully compatible with Spark's APIs. This includes Spark's SQL APIs, Spark's data frame APIs, and by extension, the Koalas data frames API. It delivers massive performance for SQL and data frame workloads with 3 important components. The first component is an improved query optimizer. The second component is a native vectorized execution engine that's written from scratch in C++ for maximum performance. And the third component is a caching layer that sits between the execution engine and cloud object storage for faster I/O throughput. Delta Engine's improved query optimizer extends Spark's cost-based optimizer as well as Spark's adaptive query execution optimizer with more advanced statistics. And this technique can actually deliver up to 18 times performance increase for star schema workloads. Delta Engine's caching layer again sits between the execution engine and cloud object storage where we build our data lakes, and it can automatically choose what input data to cache for the user. And it's not just a dump bytes cache that caches the raw data. It transcodes data into a more CPU efficient format that is faster to decode for query processing later. And with this, we can fully leverage the throughput of the local NVMe SSDs in a lot of the cloud virtual machines these days. And this delivers up to 5 times scan performance increase for virtually all workloads. For the rest of the talk, I want to focus on the native execution engine and walk you through some of our thought exercises in designing and implementing this engine. Every time when we design a piece of software for performance, it's important to look at 2 aspects. The first aspect is, what are the hardware trends? How are hardware changing and where will hardware go in the future? And that's important because ultimately the piece of software we write will run on some piece of hardware. The second aspect are the workloads. What are the characteristics of the workloads that we need to run for or on? And this is extremely important because without knowing that, we don't know what we're optimizing for. So let's first take a look at hardware. For some of you that were here 5 years ago in Spark Summit 2015, you might remember a keynote slide in which I compared the hardware spec from 2010s compared with the 2015. And I did that along 3 dimensions: storage, network, and CPU. And we found that along the dimension of storage and network, which are basically I/O throughput, the I/O throughput has gone up by an order of magnitude in those 5 years. So it's gone up by 10x, where CPU clock frequency had largely remained the same at around 3 gigahertz. So as I/Os are becoming faster and faster, more and more bottlenecks are happening on the CPUs. So in response to that, we launched Project Tungsten in Apache Spark, which is aimed at substantially speeding up execution by optimizing for CPU efficiency. It's been 5 years since 2015. Let's take a look at what has changed with hardware in the last 5 years. Interestingly, I/O throughput has continued to go up. As a matter of fact, it went up by another 10x. These days, it's really not difficult for any of us with the swipe of a credit card to launch a new virtual machine in any of the public cloud providers' infrastructure. They can give you 16 gigabytes of an NVMe SSD and with a 100 gigabit network. But CPU clock frequency remained the same at around 3 gigahertz. So as every other dimension is becoming faster and faster, the CPU become more of the bottleneck, even after 5 more years. And the first important question we ask ourselves in designing the execution engine for Delta Engine is, how do we achieve the next level of performance, given CPUs continue to be the bottleneck? Now, the second aspect, workloads. In the past few years, it's becoming more and more obvious that businesses are moving faster and faster. As a result, data teams are given less and less time in properly modeling and preparing their data. If your business context is changing every 6 months or every year and you're given some new business problems to solve, there's really no point spending 6 months to a year modeling your data, like how you would do it back in the 90s or the 2000s era of data warehouses. As a matter of fact, these days, most columns don't have constraints defined. Strings are used everywhere because strings are so easy to manipulate. And many of the columns, for example, such as date or timestamp, are just stored as strings these days. And unfortunately, a lot of this characteristics of the new workloads and the new lack of data modeling are not really benefiting the performance of the query execution, because many of the query engines are designed in an era in which data are very well modeled. And we have all learned, hey, in order to actually achieve better performance, let's model the data better. So the second important question we ask ourselves in designing the new execution engine is, can we actually get both agility and performance? Can we get great performance for very well modeled data, but also still pretty good or great performance for not so well modeled data? And Photon is actually an answer to those 2 questions. It is a new execution engine for Delta Engine designed to accelerate Spark SQL workloads. It is built from scratch in C++, so we can get maximum control of how the underlying hardware would behave in order to extract the maximum performance. And we really leverage 2 very important principles. The first is called vectorization. And the idea here is to exploit data level parallelism and instruction level parallelism for performance. And the second is we didn't want to just design something that would work very well for model data. And we spent a lot of time thinking about and so making it happen to optimize for not so well model data. Before I explain to you how Photon works, it's important for me to give you a refresher of how modern CPUs work. So we consider it a CPU 101. While we found out from some earlier slides that CPU clock frequencies are not getting higher, there are some dimensions of the CPUs that are improving, and they mostly are around the degree of parallelism. And the first is data level parallelism, and the second is instruction level parallelism. For data level parallelism, you might have heard of the term SIMD. And what SIMD does is, through a single instruction, now the CPU is capable of processing multiple data points at once. And that degree of parallelism is measured by what we call a SIMD register width. When the concept of SIMD first came out with MMX and SSC instructions in the 90s, a SIMD register width is 128 bits. And what 128 bits register width mean is that a single instruction is capable, for example, processing 4 32-bit integers. And when the AVX2 came out, the SIMD register bandwidth actually doubled. And AVX512 came out, which is the most recent SIMD instruction set. The register width doubled again. So the degree of parallelism for data level parallelisms through SIMD instructions has been doubling. And the second part is instruction level parallelism. What that means is when the CPU receives instructions to execute, it doesn't actually execute them in the order when they come in, or in any sequential order. As a matter of fact, the CPU will look ahead in this what we call out of order window, which is the number of instructions the CPU can look ahead for. And it will figure out, for example, can the CPU automatically reorder the instructions and sometimes run multiple instructions in parallel if they don't have dependency. And sometimes even running it in parallel with dependency speculatively in order to actually increase the throughput and performance of the software. And as you can see on the slides, in the past few years, with the newer generation of the Intel CPUs like Sandy Bridge, Haswell, Skylake, the out-of-order window has also been increasing. And about 15 years ago, there's actually a seminal paper published in CIDR conference, which is one of the most prestigious database conferences, called MongoDB X100. And it's written by Professor Peter Bons out of this institution called CWI in the Netherlands. And this paper really is the classic paper that details how we can exploit the maximum performance with the technique of vectorization that focuses on getting data level parallelism and instruction level parallelism. So for the past 2.5 years, the Databricks engineering team have been working very closely with Professor Peter Bons in designing what a new vectorized execution engine would look like in the 2020s with all of this new workload characteristics. So first, I want to walk you through some of the techniques we've used in Photon in order to exploit performance, and let's start with data level parallelism. The first step in designing a vectorized execution engine to exploit performance is to think about the in-memory data format. Most naturally, humans think about data in a row-oriented format. That is the first row, and then there's the values in them. But in order for vectorization to work really well, we would transpose a row-oriented format into a column-oriented format, in which case all the values for the column, for the same column, are laid out together consecutively, and that's shown on the screen here. And one of the nice benefits of this column-oriented in-memory format is when we actually do any type of compute. For example, in this case, I'm just showing you how to sum up the value of two columns. We could write a very simple tight loop here, just loop over the data and to generate a new column. And if you look at this very simple snippet of code, which actually mirrors what the real code would look like in a query engine, it's very compact and it accesses memory in exactly sequential order because it's a column-oriented format. If the data is laid out in memory using a row-oriented format, then every time when we go from one row to another, when I increments, we will have to skip a column 2, which is the list of string. And that will actually lead to worse cache behavior and worse prefetching. And the other benefit is with such a simple code snippet, what we call sort of a kernel, it's very easier for the modern compilers to be optimizing such simple loops. And you apply techniques such as loop unrolling. It's also, in most cases, the compilers can recognize this pattern and generate CMD instructions automatically for us. To demonstrate to you what that means for the CMD instructions, I compiled this snippet of code using sort of two different compilers, one without CMD and one with CMD. The version without CMD you can actually see it's pretty short. And then kind of the body of the loop, I've color-coded it to show you the body of the loop. And you don't have to understand all the actual instructions being generated by the compiler, but you can probably tell in the CMD instruction, while it's significantly longer, mostly because of loop unrolling, the instructions started mostly with the verb V, right? V. And V here basically means vectorize. It means for each one of those instructions, they are effectively processing 4 or sometimes 8 or even 16 values at once, rather than compared with the left side, they're just processing one value at once. And the performance difference of the CMD to leverage this kind of data level parallelism is actually massive. With a fully CMD code, measured even end-to-end, so with a lot of the overhead of sort of the system setup and all that, this sort of simple add arithmetics could generate 4 times speed up. So now we can process almost 8 billion rows per second just on a single core. Whereas the non-CMD version can only process, even though it's also native C++ code, can only process 2 billion. Now, data level parallelism, CMD. I want to move on now to instruction level parallelism. In order to explain that, I need to sort of bring up a slightly more complicated example, hash tables. Hash tables are one of the most important data structures in memory for data processing. It is used very frequently in aggregates. It's used very frequently in joins. Here, I'm just showing you a very simple example, as a matter of fact, overly simplified, that computes the sum for some values, grouped by certain key. And the way this would work, so very naturally, if I were to ask you to just write this code, you probably write something similar to what I have on the screen. What you would do is you would create a hash table, and then you would loop over the sort of your input data, and for each of the row, you would compute a hash bucket, and you would do a probe to look at whether the hash bucket key is the same as the current row's key, and if they are the same, you would sort of aggregate the data value into the hash table itself. So the hash table is storing a bunch of partial sums. And to simplify the code snippet, I don't even deal with key collision here. Now, if you look at this code, it turned out most of the time are actually spent in the highlighted green part, HT bucket. And the reason is the nature of the hash table means whenever you sort of scan through some data, you're going to trigger a lot of random memory loads. That is, the buckets are just random in different random locations. And random memory loads are actually very expensive for modern CPUs to do, because modern CPUs are really optimized for sort of sequential fetches, even for in-memory data. Because CPUs run so fast, if you have the CPU have to wait for some data to arrive in a random location in memory, that wait is significantly longer than sort of just doing, for example, arithmetics. When we profile this, we actually found that about 2/3, so 2/3 of the time for this code snippet, the CPUs are just waiting for memory, for data to arrive from memory. And the CPU is really spending only 1/3 of the time doing useful work. So the question now is, how do we optimize this code? In order to optimize it, we kind of need to know what's wrong with it from a performance point of view. And I've color-coded it, so the different parts of the inner loop for you. And then we soon realize it's very obvious that there's a lot of different concerns done in a single loop. We are computing hash code, we're doing key comparison, we're doing some memory lookups to load data from memory, and we're also doing sort of additions or aggregates. And when there's actually a very large loop body, it makes it, this actually becomes a very unfriendly behavior for the modern CPUs. And the reason is, if you remember what I brought up earlier, the CPUs has instruction level parallelism has a concept out of order window, which is roughly around 200 instructions the CPU can look ahead to reorder or run in parallel. If the body of the loop is very, very long, the CPU could probably only look ahead either 1 or 2 loop iterations, which means at the maximum, the CPU can actually only reorder 1 or 2 loop iterations and sort of run 2 of those, the most expensive parts of the computation, which is the excess load, do a memory load at once. So only 1 or 2. So then, understanding that, now we might have a sort of a pretty simple solution to this problem. How do we make this snippet of code fast? Even though this was a little bit unintuitive, the way to make this loop fast is to break one single fat loop into multiple small loops. And it's intuitive because we are now with multiple smaller loops, we are actually running through the loop multiple times. It seems like more overhead, for example, just incrementing I. But the reason this is actually significantly better is the most expensive part right now, the green part, is its own loop. And the body of the loop is extremely simple. And with such a simple loop, the CPU can actually, in its out of order window, can predict and look at many, many loop bodies. And as a result, the CPU can see, hey, I will need to fetch from, for example, this 12 different memory locations. And it can launch all 12 memory fetches in parallel. Instead of waiting for one to complete and launch another one, it can actually launch all of them in parallel and do all the fetches at once. And this actually substantially speed up the actual computation time of this code snippet. As a matter of fact, with these techniques, plus a number of other things, such as minimizing TLB misses with huge pages, we managed to significantly speed up this core sort of aggregation functions performance in the Photon engine. And the amount of actually wasted memory stalls have also significantly reduced. So we talked about data level parallelism, instruction level parallelism. But how does it all look if we put it all together to run through sort of traditional SQL queries? And we ran an experiment just with Photon on and Photon off, and the rest is just the Delta engine. So it already includes a lot of the great query optimization improvements that provides often some order of magnitude speedups. And we can see we actually achieved a 3.3 times speedup just at the physical execution in the engine layer with the Photon engine. So far we have talked about the techniques of vectorization. It's not necessarily a new technique. As a matter of fact, a lot of other databases leverage it. Now, one thing is sort of very different, and is we spend probably more time optimizing for the modern hardware. But the other aspect is we have spent a lot of time thinking about how we can actually optimize for the more modern workloads in which people want to sort of move faster and don't have to always properly well model data. I won't have time to actually go into all of it, all of the tricks and techniques that we have leveraged to make string go faster, but I want to give you one example so you can understand the flavor of it. When we first rewrote a set of string functions from sort of some code that runs on the JVM to native C++ code, we observed quite a bit of speedup. For example, the upper function, we achieved almost a 50% speedup, and the substring function was almost a 3 times speedup. But we didn't stop there. We asked ourselves, hey, can we do better? Now, I have to introduce you to sort of how strings are encoded in order to understand one important technique we've used. And UTF-8 is actually the most ubiquitous string encoding. Different from a lot of other encodings, UTF-8 is a variable length encoding. What it means is a single character could take anywhere from 1 byte all the way to 4 bytes. I'm showing you some examples here. For example, the character A is 1 byte, the copyright symbol is 2 bytes, the Chinese character Xing is 3 bytes, and the pile Pu, which is a legitimate UTF-8 character, is 4 bytes. The reason UTF-8 became popular and the reason they is designed with the variable length encoding is it's great for memory. A lot of the data, as a matter of fact, probably most of the data, especially in the Western world, are just ASCII characters that would all fit in 1 byte. So when you're using UTF-8, you're only wasting 1 byte per string or per character. Whereas with a lot of other fixed length schema, you might have to use 2 bytes or 3 bytes always. But unfortunately, this variable length encoding, while it's great for memory saving because it's very compact, it's actually computationally very expensive. It just takes sort of the substring functions example. In the fixed length encoding, the substring function simply returns the number of bytes. If we know, for example, every character is 3 bytes, we'll just return the 3 times however many characters we want to return. But in a variable length encoding, we have to look at each of the character or each of the bytes one by one to determine what the character boundaries are. Sometimes some databases actually give the users the option of defining what your character set is, because often some users will only have ASCII character. But we feel that's not very realistic for 2 reasons. One is users don't often actually do that because they sometimes don't even know there's optimization they can do by themselves manually. The second is often data is actually maybe, say, vast majority of the data is ASCII, but then every once in a while, so one row come in that has a special symbol, and as a result, now you're going to corrupt your data if you don't declare properly the character set. So the real question is, given the fact that most data, especially in the Western world, are just ASCII character set, but with the locations of UTF-8 beyond ASCII, can we get both the savings of UTF-8 in memory compactness and the performance of ASCII? Or put it differently, can we only pay for the performance penalty of UTF-8 when necessary, when we actually have that data? And we actually found a pretty interesting trick that we leverage in this case. And the idea is we'll actually separate any string processing into 2 steps. The first step is a fully SIMD ASCII detection algorithm that's run on the string. And this detection algorithm kernel is optimized so well, they leverage so it's handwritten with AVX instructions. It can run at 60 gigabytes per second per core. So this is almost running at memory bandwidth. This is so fast that it's negligible overhead in virtually all cases. And the second step is depending on the result of the ASCII detection. If we realize a string is really just can fit in, the entirety of the string can fit in the ASCII character set, we can run the special fixed length version of our string function. Otherwise, you run the variable length version. And with this technique, we achieve an order of magnitude speedup for most of our string functions compared with the original JVM variant, and in many cases, even compared with the SIMD version of the C++ variant, when the data are, for example, does fit in the ASCII character set. And this is done without the users having to manually do anything. It's just an automatic, auto magic algorithm. For example, upper and substrings are significantly faster. But this is just one technique. I want to show you, there's one more example, which is regular expressions. It is used pretty frequently when people are dealing with or massaging data. It's very rare you will see regular expression showing up in the actual benchmark, but we have found the use of it in the wild so much that we've spent a lot of time optimizing it. As a matter of fact, regular expression in Photon is more than 4 times faster than regular expressions elsewhere. Just to wrap up, Photon is a purpose-built execution engine for maximum performance that's built in C++. It leverages vectorization so we can take advantage of the data-level parallelism and instruction-level parallelism presented by modern CPUs. And it's also really designed to optimize for modern workloads in which there's a lot of strings everywhere. And I've shown you some examples of that. And to conclude, Delta Engine delivers best-in-class performance with all the expressiveness of Spark. It has 3 important components: a query optimizer, an execution engine, and a state-of-the-art caching layer. Both the query optimizer and the caching layer is available now on Databricks. And you can actually contact us to get access to the new execution engine that's called Photon. And thank you. I would like to pass the talk back to Ali.
Thank you, Reynold. So this is great. This assumes you have your data in Delta Lake. But how do you actually get it into Delta Lake in the first place? I'd like to spend some time to talk about that. So at Databricks, we have something called the Data Ingestion Network. Data Ingestion Network is tightly integrated partnership with things like ADF and companies like Fivetran and Stitch. When you go inside Databricks, there's something called Data Ingestion Network Gallery. When you click on that, you can now see an icon of all the different operational databases that an organization might have their data in. You click on it, and it can now automatically transfer that data into Delta Lake. But we also want to make it easier for you to get data that is in a blob store into Delta Lake. Before, all of this was manual. You would have to manually connect to a notification system, register that whenever files appear, please kick off a job scheduler that then runs maybe a Spark job that takes that data and converts it into Delta Lake. Well, what we've done is that we have now something called the autoloader. The autoloader automatically connects with the underlying notification systems and figures out when new files appear and automatically convert them into Delta Lake. So that's awesome. Now you have all your data in Delta Lake. But how do we actually keep this secure? So in Databricks, we provide fine-grained access control on top of Delta Lake. This is standard SQL-based DCLs. You can now submit revoke and grant queries in SQL. You can create groups and add individuals to them. And it tightly integrates with the cloud vendor's Active Directory. That means you don't need any passwords or tokens or certificates. The identity goes from the Active Directory straight to Databricks, and then you access the files seamlessly. So let's put all this together. So we talked a lot about how Delta Lake solves a lot of this complexity around managing data, and how Delta Engine improves the performances of all your analytics workloads. But once you have all the data, there's only a handful of analysts who have the tools to make sense of it in an organization. Zooming out, data teams are a small part of the equation. In most organizations, we have organizations like marketing, HR, finance. They don't want to use Python or SQL or Scala. Today, to consume data, the rest of the organization has to really jump through lots of hoops. If we want data teams to truly unite, we have to make it easier to consume that data for the rest of the folks in these organizations. Recently, a really fascinating open source project has emerged that's starting to solve these problems. Redash is an easy-to-use open source dashboarding and visualization service for data scientists and SQL analysts. With it, data teams are better able to democratize sharing data across and within organizations. The community behind this project is absolutely amazing. This project started in 2013, just like Databricks. They have over 300 open source contributors, and they're really passionate about democratizing access to data across organizations. And it's working in a really, really big way. Every day, millions of users and thousands of organizations around the world are using Redash to get insights and make data-driven decisions. They've seen a ton of success, over 7,000 deployments around the world, and the engineering team standing behind this great project is absolutely fantastic. And they've built something great that aligns completely with the Databricks values. So it's my great pleasure to announce today that Redash has joined Databricks. And we're super excited to align these two open source communities, the Spark community with the Redash community. To tell us more about how this will work, it is my great pleasure to introduce Arik Fremowicz, the founder of Redash. Arik?
Thank you, Ali. I'm really excited to be joining both Databricks and the larger open source community of Spark. 7 years ago, I started Redash as a hackathon project, and I didn't expect to be here today sharing the story with such a large community. Back then, we just moved our data into Data Lake, and we needed somehow to use the data, so we tried some SQL Workbench tool, and this was really missing collaboration. We realized that what we need is some web application where we can type in the query, get the results, visualize, and share them. And I decided to give it a try at that hackathon, and that's what started Redash. Working with Databricks earlier this year, I realized how much alignment we have on a lot of these core ideas that I had when I started the project. Make it easy to collaborate with others around the data and democratize data for all the teams. But beyond the product and vision alignment, it's the amazing culture at Databricks that really makes me and the team excited about joining Databricks. Now, let's talk a bit about what Redash actually is. So, Redash gives you a SQL interface to query your database in its natural syntax. But we give you some tools to make it easier, like the schema browser, autocomplete, and query snippets. Now, once you have the data that you queried, you can visualize it with a wide variety of visualizations, and then group these visualizations into dashboards. You can also set up refresh schedule so that you get the most fresh data without waiting. And when it comes to databases, Redash has you covered. So Redash supports about over 40 types of databases, data warehouses, data lakes, and different types of APIs. So it's likely that whatever data source your organization uses, you can connect it to Redash. Now, let's check out how you can use Redash with Databricks. Let's say that I'm a data analyst in a SaaS company, and I'm looking to help the business understand revenues, usage, and how to drive conversions better and reduce churn. We have at least 3 types of data: account data, payments data, and usage data. But this data is coming from 3 different sources. Accounts data is in the operational database, payments is with the payments processor, and only usage data is in our data lake. For many meaningful analysis of the data, we will need to join the data from all 3 sources. We can do this join in Redash, but this has limits and performance issues. What we really want is a single source with all the data. And this is exactly what we can achieve with the data lake. Now, all of our data is in a single location, and we can easily use the data together to create more meaningful insights and have the most fresh data. And now, with that intro, let's check out the actual demo.
Right, so here we have the Redash query screen. And let me type in a query to just show you a bit how it works. So I have the autocomplete helping me a bit here. Although it doesn't save me from typos. Now, here on the left, we have the schema browser that shows us the tables and their columns. Now, we got the data back. We can look at it, but it's much nicer to look at the visualization. It's easier to understand this way. So let's create one real quick. So here we see the trend of our monthly recurring revenue over time. And we can see that it's growing, but we don't know why or how it's growing. So it probably makes sense to see a breakdown of what's contributing for it. So let's create a bit more complex query this time. So this one is a bit long, so I'm using query snippet for it. Now, a query snippet is a very simple construct. You have this keyword that triggers it, and you have a definition of what the snippet will be. And then when you trigger it, it gets inserted into your query. I got the query back, and this time I have much more information, but again, a visualization can really help understand it. So here's a breakdown of our monthly recurring revenue. And we can see that most of the time it's growing due to new monthly recurring revenue, but we had some successful campaigns around expansion in a few months, and we have some regular expansion over time, and unfortunately, we also have some churn over time. Now, from the same set of data, I can create some other visualizations, like, again, the growth of monthly recurring revenue over time, some counters, and the average revenue per user over time. Next, once we sometimes would like to look at this data at a daily level. So here we have another visualization that's showing us a rolling window of 30 days of the monthly recurring revenue at that day. And that's useful when we want to track it in a more real-time fashion. For example, when we're running some campaign or we are aware of some issue that we want to track more closely. Once we have a few of these visualizations, we would like to create a dashboard. In these dashboards, we see different facets of our monthly recurring revenue, like this breakdown that we saw before, the growth over time, breakdown by different plan types, and breakdown by geography. Now, looking at the revenues is great, but we also want to help our customer success team to help drive this revenue forward. So here we have a dashboard for our customer success team that shows them 2 types of accounts. One type is promising trial accounts. That's basically accounts that are currently in their trial period, didn't convert yet, but showing good indication of usage. So we might want to reach out to them and help them switch over to a paid account. On the other hand, we have the paid accounts that showing a decline in usage, where we would like to reach out to them and see if we can help them get back on track. To help the customer success agents, each row here is a link to this other customer insights dashboard. And this dashboard is using a parameter to filter out and show us only this account. Here we can see some details about the account, like their usage over time, type of account, the number of widgets they created, and we can definitely see the decline. And we can drill deeper to understand why it might be, or just reach out to the customer. Now, this was a really quick taste of Redash. We have a more in-depth session later today that I recommend you checking out. Thank you very much, and back to you, Ali.
Thanks, Arik. I'm super excited about this integration. So to zoom out, in summary, we have Delta Lake as a structured transaction layer on top of your data lake. It allows you to overcome a lot of the challenges that data lakes have historically presented by using ACID transactions, indexing, fine-grained control, and schema validation and expectations. So that's the Delta Lake project. Then, to ensure that you have all your analytic workloads and that they can be executed really fast at low latency, we have on top of this Delta Engine. We think Delta Engine, with its vectorized query engine, query optimizations, custom connectors, combined with all the enhancements that substantially improve performance and price for analytic workloads, make Databricks the ideal platform to deploy Delta Lakes. And finally, all of this comes together in the ways that data is actually made useful. Redash is going to simplify dashboarding for many analysts and data scientists. And tomorrow, we're going to deep dive into how enhancements to MLflow, the open source end-to-end machine learning platform, will make Databricks Workspace even better. And I'm really looking forward to what we have to share there. The data workloads and the data platform working together end-to-end is the heart of Databricks Unified Data Analytics and our vision for data teams. To share how this vision is coming to life within Starbucks to drive collaboration and innovation, it is my great pleasure to introduce Vish Subramanian, Director of Data Analytics and Engineering. Vish, what's brewing at Starbucks?
Thank you, Ali. Hello all, welcome to Spark and AI Summit 2020. My name is Vishwanath Subramanian. I'm the Director of Data Analytics Engineering at Starbucks. As Ali mentioned earlier, as we're all navigating through these challenging times, we strive to make fact-based decisions with data. I'm here to talk to you about our data journey. At Starbucks, our mission is to inspire and nurture the human spirit, one person, one cup, one neighborhood at a time. You may be familiar with some of our 30,000 stores worldwide that may be a part of your experience. We have over 30,000 employees who we call as partners who ensure our standing as one of the world's most admired companies. In order to adhere to that quality of service and product, the key focus areas that we focused on are making sure we have elevated partner and customer connections, breakthrough in beverage innovation, and also accelerating our customer engagement across channels, including digital. However, this story is driven by our ability to harness data to power these customer experiences. Amazing teams across Starbucks continue working on the next breakthrough innovation to ensure we build the right customer experience and an enduring brand appeal. These extend across our multiple domains: partners, products, store portfolios, and digital. There are tons of awesome teams working on big ideas and enabling them to be brewed at scale. As much as it's about the product, it's about elevating customer connections and the experience that is driven by the convergence of data. For example, on mobile, we use rapid A/B testing to improve recommendations using reinforcement learning models on the Brewkit platform. On drive-thru, we cross-sell modifications using engines like Deepbrew. On store applications, we serve near real-time transactional data with billions of data points to internal reporting applications so that actual store personnel can monitor transactions near real-time. More importantly, data is extremely crucial as we extend channels for delivery and new norms in today's new era. The ability to serve these use cases is only possible through a sound data strategy. Our data strategy and guiding principles are built on three pillars: single version of the truth, providing trusted store of information across customer, product, and stores; data analytics enablement, as well as trusted data to ensure data quality, privacy, security, and the right data definitions to access this data. However, to execute on this strategy, we had to deal with several modernization challenges. On the architecture side, we were dealing with petabyte scale of data and fragmentation across systems. On the ingestion and processing, the ability to process near real-time data products and a huge variety of sources. The inability to implement updates, merges on fast-changing data in an optimal fashion. Also, non-optimal engineering experiences with services that did not perform at scale, for example, taking a long time to provision or scale. Also, on the consumption side, there was no real single source of truth, a lack of a unified user experience, and an impedance mismatch between data and model development and operations, blocking experimentations and reproducibility. To illustrate how we dealt with all these challenges, Brewkit was our zero-friction analytics framework. This is built on a strong foundation of Azure, Databricks, and Delta. Brewkit would be a unified analytics platform to reduce our impedance mismatch between access to data, ability to perform data science, and operationalization. We wanted to make sure the smallest of teams at Starbucks have the ability to do at-scale data science and data engineering with this framework. Brewkit, our massive scale data framework, has all the necessary capabilities in a box to perform at-scale data science and data engineering. We leverage multiple Azure services and homegrown Starbucks engineering to light up a functioning environment. Multiple SKUs translate into data engineering and data science templates, all this generated declaratively in a matter of minutes. We have services like MLflow and Azure ML that help power our model management lifecycles. All this backed on storage services such as Delta Lake. We use Azure services such as Azure Key Vault to help us secure key management across different environments. From an infrastructure essential standpoint, we have Databricks as the core engine for on-demand compute, and the notebook collaborative experience helps teams collaborate and experiment at a rapid fashion. The AI serving layer is powered by services such as Cosmos DB that help us enable internet scale, low latency serving. We also provide automation and starter notebooks and templates across a variety of use cases so that users can bootstrap quickly onto the environment. All activities are audited for governance reason as well as return on investment. Moving on to our second challenge, data and ingestion. And huge focus areas for teams has been to ingest data at scale using custom Spark utilities with massive parallelism. With the inherent benefits of Delta, such as asset transactions, metadata handling, and schema enforcement, we can use services now like Azure Event Hubs and Spark Structured Streaming that help us process millions of transactions at scale per second. For long-running pipelines, fault tolerance is trivial now with structured streaming. More importantly, Delta has now helped us build out our historical data and live aggregations together to make sure we are now giving our store partners real-time insights on data based on history and on current time. Consider pipelines that hold transaction data that are cleansed, audited, and processed to be sent right back to the stores within minutes to ensure that our partners have this latest data to make decisions with. The ability to perform stateful and stateless aggregations helps us tailor trade-offs based on use cases. Features like compaction, auto-optimization, help us now have the right partition keys in our partition data lake to get us 50 to 100x performance gains as well as storage optimization. It's crucial for us to support time travel and version data for data and model provenance. Operations on Delta, such as merges, updates, and deletes, help us build out our own anonymization frameworks. We can also have logical separation on the Delta layer with discovery and integration zone, where we can apply schema enforcement based on the source of the data, as well as apply retention policies. This translates to a highly industrialized process where we aggregate data across different zones and load data from a variety of sources, using the workspaces, clusters, and job APIs, and orchestration tools like Airflow. We have predefined patterns for these ingestion processes that help us define retention policies as well as partition according to the use case. Features, Delta helps us with features like idempotency, with merge operations, and with fast change data capture use cases. Time travel provides snapshot isolation for fast changing tables. We also we make sure we're now governing an enterprise data lake with the right permissioning and access control. Overall, the strategic view has been here to commoditize data ingestion to such an extent so that the teams can focus on business problems up the value chain rather than focusing on moving data from point A to point B. On the consumption side, which was the third challenge we had, We wanted to make sure your experience is as good as you walk into one of our premier experiences. We serve over 50 plus workspaces on the enterprise with different business units with logical separations between them. This gives us flexibility to monitor, secure, and segregate these environments based on the use case. We also run our own version of our metadata sync process across these 50 plus environments to sync across these workspaces at scale. So all users are looking at one governed version of published data with a single source of truth. The successful data enablement and Brookit journey has now led us to focus on our AI/ML strategy. We have enabled convergence of data and enabled Brookit for the creation of models. In the past, our goals were to deploy environments in a matter of minutes, to deploy data pipelines in a matter of minutes, which we have largely achieved. Now our focus is now to democratize machine learning, and how do we enable our data scientists to enable machine learning models in a matter of minutes. We have our framework AI Reserve that we are in the process of deploying with a goal to achieve exactly that. Powered by MLflow and Azure services, AI Reserve will be guiding larger constructs in our enterprise, including a model marketplace. This will be used in many use cases across the board, such as store operations, quality of service analysis, personalization experience, and much more. The ML stack comes together with analytics out of the box with our Brookit environments. Users have a plethora of environments that they develop their code in. We can use version control to deploy builds based on integration with Azure services like Azure DevOps, based on use cases like on-schedule or drift scenarios. Users can use Azure ML or MLflow for their model lifecycle management, and all this backed on a persistent data store on the Delta Lake. We also make sure our AI Reserve integration allows our data scientists to containerize their solutions and use Azure Kubernetes services to essentially serve our REST APIs, which leads to the larger construct of the AI Reserve model marketplace. Today's real-time data, along with third-party data, is driving our decisions across the board, including store reopening strategies. All this is being supported by a unified data and AI solution. We now have petabytes of data located on Delta Lake at massive scale, hundreds of data products built on Spark, an average deployment time of pipelines and environments in minutes, over 1,000 plus pipelines across engineering and user workspaces, and more importantly, these are all highly reliable and fault tolerant. From a data team collaboration and productivity standpoint, this has been huge. The tooling is collaborative. We also now foster a culture of experimentation and self-service and maintain shared responsibility across our environments. And the focus is now on outcomes and not technology or infrastructure. I would encourage everyone to check out additional talks by Starbucks at the summit, including how we operationalize our big data pipelines as well as our machine learning. Please be sure to visit stores.starbucks.com for latest news and initiatives. I hope you have a great Spark and AI Summit 2020. Thank you very much. Back to you, Ali.
Thanks, Vish. And I also want to thank all the speakers and the demoers today. And before you go, a few things I want to remind you of. Please attend as many of today's breakout sessions as you can today. Tons of interesting content and speakers can be found. Visit the Dev Hub and the Expo for live demos and engage with our technology partners. Network. This is a great opportunity to meet and learn from thousands of people like you. You can head to the Advisory Lounge, Birds of a Feather networking experiences, theater sessions, and my personal favorite, Ask Me Anything sessions with Matei and other industry leaders. Share your thoughts, lessons learned, and selfies on social media. Be sure to use our hashtag SparkAI Summit and data teams. And finally, please join us to support the Center for Policing Equity and the NAACP Legal Defense and Education Fund. Click Donate Now in your dashboard, and Databricks will match all donations up to $100,000. You can hear directly from the founder of CPE, Dr. Philip Atiba Goff, along with Professor Jennifer Chase from UC Berkeley and Nate Silver from 5:38 in this afternoon's keynote session. You don't want to miss this, so be sure to join us at 1 p.m. Pacific time. I hope you found today's session informative and hope you enjoyed the rest of Spark and AI Summit 2020. Thank you.
Bye.